Mark, do you want to introduce?
Sure, yeah. So, welcome to another episode of Composability. Like, it's my great pleasure to have like Chanchi Chen speaking to us today. Chanchi doesn't need an introduction, but just in case you don't know who he is, Chanchi is pretty much like one of the founders of the field of ML systems. His projects included like a lot of stuff, like ranging from like XGBoost, like MXNet, uh, and today, like him and I met like at MLSys like earlier this year, and he was like talking to me a lot about like his sort of early rumblings around building an open ABI for ML systems and standardizing like foreign function interfaces. We had a really nice discussion, but like I really wish more PyTorch people were on that call. I see a lot of these people on this call today. So I guess like Chanchi, you should get started. And folks, if you just want to ask Chanchi a question, please just quickly introduce who you are, like what sort of subpart of PyTorch you work on. That way, like Chanchi knows who to reach out to after this call. So yeah, Chanchi, please take it from here.
Yeah, thank you, Mark, and thank you, Ed, for hosting me. It's really great pleasure to be here. And today I want to tell you a bit about something we've been doing recently, but I want to first set up the stage, right? So the reason why I was really excited to be here is that, we are still in this early stage of the development, and we do believe like PyTorch is the first class concern, and we would love to find ways to collaborate and learn from insights from you guys and working together to lead and co-evolve this thing. So feel free to interrupt me for any questions. I will try to make it short so that we can spend more time brainstorming and go from there. Okay. So I can share the slides later, but let me see. So can everybody see the slides? Yes. So okay. So the talk is about building an open ABI and FFI for machine learning systems. So if you look at the machine learning system landscape today, I think it's kind of on one end it's kind of thriving. We have a growing number of DSOs for good or bad, where we have Triton, Helium, Thailand, QTalk, QDSO, and all these amazing deals coming out for us to be able to bringing in all those state speed of light kernels on different environments. AI agents start to be able to write kernels that hopefully will be integrated back, right? Compiler uh, start to play a very interesting role, but I think one big lesson from PyTorch compiler and other community learned is that compiler really need to interact with the runtime as well. Like compiler no longer is more like standalone thing. You compile, everything sits in that language and so on. And we also start to see, different components on the left-hand side needing to interact with different components on the right-hand side. PyTorch and Python is certainly one of the biggest consideration here, but also we also have environments like automotive where we kind of need to ship kernels to TensorRT that get shipped autonomous drivings, and in that case, we need to get rid of Python. And there are other attempts on building graph compiler variants on being able to improve these things. And all these things kind of brings this kind of interoperability challenges in terms of how each of those components can talk to each other, right? Today, the approach we do is we do a specific pair or bring up. So for example, when we're bringing in like flash infer, we'll support like PyTorch bindings for flash infer in general. And when you have a DSO, so you want to think about how do you expose that DSO to Python, PyTorch, and other environments. So fundamentally, the interoperability challenge kind of boils down to what we call an ABI and FFI challenge. So what are they? First of all, the ABI kind of defines how data are being stored in each framework and what occurs when functions called. For example, it would be really ideal that we could pass a torch tensor and maybe at some time point, getting some routines in QPy or QDSL, and they will be able to directly, pass torch tensor as a pointer and directly being used somewhere. However, today, there is still some gaps there because different frameworks for some historical reasons, they kind of ended up have their own different variants of data structure, right? So you can not really directly, pass the pointer from one to another. It's also kind of like a foreign function interface concern, mainly because today, like, we kind of mandates cross-language interoperabilities. A very obvious example is, C++ and Python, right? More recently, there are some attempts on doing Rust as well, where, you have most of the things in Python, but you need very fast C++ extension to be able to interact with the Python. Every DSL themselves can also be viewed as their own mini language because you kind of always need a mechanism to be able to interact with other things like PyTorch, Python, and other things. So based on this, And we have this kind of thriving ecosystem where so many components acting and evolving together. There are possibly two way out, right? One way is maybe let's create one unified programming language that replaces everything so that we don't have to go across the boundaries. But today's ecosystem do not work in this way. So another way is fundamentally, we think the interoperability is here to stay. So that ideally, we want to be able to make ABI and FFI a first class concern, so that we can make it a bit more easier. However, doing interoperability for general purpose thing is really hard because that effectively means that you are kind of still fall onto this problem of developing general purpose languages. So we are kind of focusing on AI ML system needs, and I think there's some hope in here. So specifically today, I would like to introduce TeamFFI. So it's a minimal standalone open source ABI FFI. We developed it for machine learning system. So it's kind of evolved from our past several years of iteration of ABI in TVM. But as of today, our clear intention is we would like to bring it up as a standalone minimal repo so that it's very independent from specific compiler or framework, and it's meant to be used across compilers, custom DSLs, runtime libraries. So the key elements includes we use standard tensor ABI so that we can have a stable tensor in memory representation based on DLPAC. There's a compact value and function convention so that we can make sure that different functions from different frameworks can be easily exchanged across each other. And more importantly, we would like to have first-class PyTorch support so that we can handle things like error propagation, stream context handlings, and natural cross language support so that we can work on Python, but if necessary, we can also ship to environments like automotive and other environments. So at the high level, here's how it works. So I'm going to give one example on a kind of a work in progress. We are kind of bringing in this flash info library to be built on this mechanism. So say we have a library extension that we like to expose to the ecosystem. All we do is we will have a function that being defined here, where we have inputs as FFI tensors, and then there will be the function will be able to obtain the stream from this environment call called get environment current stream, and then you're going to launch a kernel here. And then there's a micro in C++ that allows us to define the function ABI so that effectively this function will be exported through the ABI convention that I'm going to talk about in the next slide. And then this will give us the agnostic dynamic libraries being JITted or ahead of time compiled that come with minimum dependencies. So it will not depend on Python ABI or Torch ABI. It will only depend on minimum stable libtvm.ffi.so that's around 1 megabytes, or even can still be further minimized if there are resource constraints, and shipped by pip, stable or bundled in C++ runtime. So at runtime, what we do is we provide different kind of mechanisms you can use it. For example, you can load the module from the same SO, create torch tensors, pass it in, and use the normal torch function. And also, we will be able to directly use the non-Python environment. So we will be able to load it in from here and call sample. Effectively, it's kind of like a overall convention that allows us to be able to kind of package this machine learning related functions and kind of make sure different frameworks talk to each other using this interface. So under the hood, the API kind of looks like this. So this is a minimal C example that explains what happens when you kind of hit a function that's being defined through this convention. So specifically, we have this, all the functions being exposed in this convention will have the same function signature. So you're going to have a handle which corresponds to the closure callback, arguments. I'm going to talk about more next is the type erased version that is a text union that encodes all arguments, number of arguments, and result that's used to be pass a result back. Okay. And this is the C code. So ideally, if you are writing a compiler that want to generate function like this, it's pretty reasonable and easy to generate a shim like this. And then what you do is you're going to read each of the arguments. So in here, what you do is for each of the values, you track if the type index equals the tensor index. If not, you are going to report a actually it should be a type error, right? So it's because it's so you can set the error in the environment and return a -1 that returns back where the caller will get a Python exception back through this error. And then you're going to read a DL tensor, which is a tensor data structure here, and run your computation. Right? So effectively, for a DSO to be able to expose the function through this ABI convention, what we need to do is have this OR stream here, and then plug in the DSO generated coding here. So this particular example, actually, I'm going to show a link later. It can be played on the code, and effectively just need to compile it. You can also use LVM to generate a .o file that looks like this, and then get your SO file. And when you load it back, effectively, this mod.add1c will be able to directly invoke this particular function signature and run all the underlying computation here. Okay, so and several things we did to enable like first-class PyTorch support, right? So first of all, when we have this function, like when you load a module, you create torch tensors, you pass arguments in. First of all, it's going to live translate the torch tensor onto the FFI ABI tensors via DLPAC. And then we also try to detect torch current context streams so that effectively within the function, you can call this get environment stream to get the current stream. So that particular function is going to work with the current torch stream and work with the CUDA graph capture. And also we are trying to preserving allocators so that when you're allocating something inside, effectively directly maps to torch allocator so that torch will be able to kind of take charge of all the memory management. We spent quite a bit of effort optimizing the FFI overhead here. So overall, if you have a function that takes like X, Y, Z, 3 arguments as torch tensors, the API overhead is around 400 nanoseconds. And for reference, if you just do a Python call with no op, the kind of best you can get is around 0.1 to 0.3 microseconds. So we're very close to kind of a speed of light limit here using this convention. And if you are doing it in C++, the overall overhead can be kind of minimized to even further, right? Because you don't have to go through a Python environment. And in that case, the best effort of just the function call overhead is getting as close to like 10 nanoseconds and can be further optimized if we do something like cross-function inlining and so on. So, and I'm going to unpack a bit further on the technical details here, right? So, but I will be also more than happy to open up for discussions and dive deeper. There will be a preview there as well. So there are kind of 2 ABI structure here. So first of all, we need a tag union any construct that allows us to be able to represent any values. I think it's very closely related to the torch I value, if I remember correctly. Or where we kind of store different values here. There's a type index that indicates which type it is, and then followed by a union field that stores different kind of data. Most of the port types are stored on stack, and then there are objects that are stored on heap. And we try to support most of the types that meets the MLAI needs. So that includes port types, stream bytes, tensor, function, which is a very important construct that allows you to get Python callbacks and other things. Then any function that you return can be passed as argument as function as well, and device, dtype, and array and map. And there's also dynamic mechanism that allows us to extend the kind of objects that can be defined in here. Another thing is that when for tensors and other bigger structure, we use a reference counted object that's effectively almost same as C10.intrusive pointer here. It contains a type index that indicates the type same as the f of any, a weak reference counter, and strong reference counter. And it also comes with a standalone deleter that's being embedded in the object so that a particular object being allocated in one language or framework will be able to safely delete it in another language or framework very easily. So you can envision that even in the future, you could return an object from Rust, for example, and run that deletion on Python or on C++. And we try to kind of compact it so that the overall header is around 24 bytes, and the overhead is reasonably minimal and almost the same as what you will do getting an intrusive pointer here. Okay. So I can elaborate a bit of possible thoughts on how FFI can be used. I think it can be very useful for library extension exposure, where we can have a Python agnostic wells as well as AOT module that can ship to non-Python. There are opportunities for compiler runtime interopt. For example, in a lot of cases, compiler might have needs to interopt with more DSLs. And ideally, each of them should have, if they have a single convention, you don't have to do bring up for each pairs. It gives you flexible callbacks on the other components of Python and mechanisms like error interoperability so that you can throw structured error back to Python. It's also very useful for packaging DSLs where you could generate a function that follows ABIs, and effectively that gives you automatic support for first-class torch, and out-of-box support for also things like executors that interface with ABI. And the goal here is really being minimum so that the compiler and firmwares can do all the magic, but define a set of interface so that we can get everybody to work together better. So,
sorry, quick question on the previous slide. Can you give more details on unifying the packaging for both JIT and AOT? What do you mean by that?
Yes. So particularly that means that effectively when you do AOT, right, you will be able to just expose your functions in the convention, and that gives you ability to be able to kind of like directly get an SO file that can be loaded back later, right? But in the same time, the same convention, you could use that for JIT, where you could JITting kind of different components and even put them together, because you could envision that, for example, you could have an NVRTC that give a device-only memory, a device-only function, right? That contains the FFI function that host function calls onto. So it kind of simplifies some of the JIT use cases as well. Yeah. If that answers your question.
Yeah, that's okay.
Yeah. Okay. Yeah, and I will show links so that there are examples that I will be more than happy to find time and discuss further on all the topics. Yeah. Okay. And then, so the current state is that we are still in semi-private mode. So we have the repo already up. ABI is recently stable, and we are kind of in a mode of sharing with early partners and collab. And more importantly, I think my goal here is really trying to find opportunities for collaborations and also working together on this. And we are also working on nice feature improvements, like loading line is really nice from PyTorch that we find really useful. NVFTC support, and we're also looking into possibly support other languages like Rust. And following that, the plan is we would like to know about folks' feedbacks, going through a public RFC period so that we can evolve it and make things better for PyTorch and the other frameworks working with this, and then do a stable release after RFC period so that we can start with semantic versioning, and ideally the ABIs remain stable over time. Yeah. And yeah, so I also have some preliminary Stroma ideas on possibly working with PyTorch. They are like ranging from very low hanging to maybe a lot more involved, right? So I think definitely ideally enabling fast exchange mechanisms upstream. So right now we relied on JITting a load inline module in Torch to be able to do that fast exchange through C++. And finding ways to leverage FFI for DSL kernel packaging exposures. We'd love to have first-class support into Torch compile so that Torch compile kernel can invoke those ABI conventions out of box, and possibly long shot align more on the structured ABIs, reference counters, and tensors, so that and to make things work better for Torch as well, and any ideas that would involve the ABI better for PyTorch use cases. And I will stop here. So there are links and examples in the preview doc, and I would love to connect. I'm on PyTorch Slack, and I will come in person in PyTorchCon and give a talk related to this on the AI Infrastructure Summit. And I will stop here, and feel free to ask any questions and brainstorm ideas. Yeah.
All right, questions from the room.
I think Ed, it would be good if we give Chenki an intro on what we're doing as well on the ABI side on our end.
Yes, so
Is
that
that
was
okay?
also what I thought. So Jane, yeah, are you ready to
Yeah.
talk about our? So in particular,
I
I'm very interested in you pointing out what the differences in design goals between our ABI stable effort is.
Okay. Okay.
Like as you can tell from the presentation.
Okay. Yeah. Love to do that.
Yeah. Well, Jane. So Jane's going to talk a little bit about what we're working on in ABI stable.
Yeah, I think that will give context, and then we can have
Yeah.
a bit more of a discussion.
Mm-hmm.
Okay. Yeah, also to just give a disclaimer, Tenchi, I feel like I don't necessarily know exactly how these things overlap or not, but a lot of the implementation seems quite similar. But I wanted to give you a high level idea of what Torch is doing. So we've also noticed the ABI problem because we have custom ops, or my first focus use point is like CUDA kernels, like flash attention or whatever, like for them to be able to build in a way that does not depend on the libtorch.so version. So that's where we're coming from. And with that, we have been rearranging how the libtorch library looks like. So even before I started, AOTI, which is like our compiler team, has already started building a shim. And the shim is similar to your like C-level API surface. So I think I'll just go through the diagrams because I think they're the most clear. But you can imagine libtorch.so as like red, and it implements two types of headers. There's like the most like majority of Torch headers, they're not stable. There's no promise on them. There's no guarantee. They can change. But we also have a small subset of C-style shim APIs that we've basically said, hey, look, we're freezing them. We're not going to change them in the future. This is our shim for now. And if you're curious what lives in that, we have a shimified version of Tensor called A10 Tensor handle. We have like Tensor get size, like all of those things people might care about, like data pointer. Those APIs do exist. Okay, I'm gonna move on. And then because the C-style shim is not very pretty, like you had also noticed, we're like, we should make that easier. Oh, okay. And then, before I get there, there's one more thing, which is just like libtorch also has a lot of components that do not need to depend on Tensor or any of our structs, and they can just live in headers. And if they just live in headers, we call those header only basic components. And since they're header only, there's no .so attached to them. Anyone can use those and be independent from libtorch. So the ABI problem is not really there. That's just to put that disclaimer on there. Okay. So yeah, before 2.7, basically all custom kernels went through the unstable headers. With 2.7, we've actually built out a way to have these custom kernels use the shim APIs. But even then, we think that it is not the most clean for we don't really want people to call C-style shim APIs. It's kind of not fun. So we've been building out a high-level C++ API that promises to only use the shim or header-only APIs. So today we actually have APIs for like Tensor and also some device utilities like CUDA Stream, CUDA Guard, and a way to connect to the PyTorch dispatcher. So that's and a bunch of A10 ops. So I think that's a good summary. I can also go into more detail of like concretely what those APIs look like. But let me pause there for anyone's questions.
Tianxi, do you have any direct questions?
Yeah, so I tried to do a bit of homework right before coming here. So I did read the A10 stable tensor implementations. I would love to. So I think in terms of like the goals, right? I think there are definitely overlapping goals, and so we all realize that ABI is the issue that we would like to solve, right? So I can see. Maybe let me start with how I see the TVMFI current design can help or can provide a bit of additional bits besides the overall A10 part. So
actually, maybe I want to ask a quick question. Actually, in terms of the high-level goal, before we dive in there, I think there is a slight difference in the goal in the sense of like from where we're coming from here, the goal is to say we have a lot of people building custom kernels in the PyTorch world.
That's right. Yeah.
And our goal is to actually simplify the life of these people in terms of their packaging, the distribution, and all of that. Yeah. I think that means in particular, as opposed to what you were talking about, which is like in any kind of world, I think we do have the scope of what we're going to do is potentially a bit more in the sense that there are a lot of utilities that these people use in these kernels, and a lot of information tools coming from the libtorch code base that we do want to make available to them.
Yeah.
As we're assuming they're not writing a pure CUDA code.
Yeah.
We assume they're gonna want things like the D types we use, things like the dispatcher, things like I'm blanking on ideas, but a whole bunch of these things basically we're exposing from core that might be out of scope for you if you're expecting them to write a plain CUDA kernel where the only thing they use there is, just a tensor object, a couple D type, like the 3 or 4 types you mentioned, and then they use CUDA as is.
I think that's a fair comment. That's why I think, what I'm talking about is a lot more lower level in some sense, right? So I think that I'm talking about low level mechanisms, but on that end, I think that I want to find synergies and working together so that hopefully this low level mechanism can also enable some of the stable ABI effort here, if that makes sense. Yeah. So I think in terms of lowest level mechanisms, there are one thing that I think is certainly could be useful in terms of how do we encode a generic function, right? That can be go across ABI boundaries, so that effectively this like a tagged union concept of bringing in the FFI any, where you could have things like of course tensors and other things, but also being able to have like a function and other objects being part of that tag union any. I think that is something that could be helpful in some sense. In terms of like yeah.
Are we muted? Oh, we're not muted right now. Yeah, well, as you're saying that, I was like, okay, well, in PyTorch, we have these things called I values. And then as a part of this work, we also built out stable I values, which is just like a representation. And let me see. Okay, so like this table is like every type we ever have in a schema. So like device stream, tensor, like scalar, all these things. And then this is old. And then their actual implementation in stable I value representation and also what we expect the user to use. And I'm expecting there's quite a lot of overlap in how FFI is also doing that.
So there is one more thing on top of that which you might want to mention, which is the AOT dispatcher.
Oh yeah, okay. And then for our A10 ops, we've actually developed this. We have a way to call it into the Torch dispatcher. And I want to show. I want to find. Wait, I want to find like the API for this. Okay, maybe I will have a better link soon. But basically, the way it works is we take in a stack of stable I values, and then we pop them off and translate them to based on the schema, so that we can actually call the actual op. If that makes any sense at all.
Yeah,
so it's similar to it's similar to your type checking thing of like, oh, is this a tensor? If so, okay, great. Like cast it as a tensor, move it along. We have something similar with our I values as well.
Yeah, so I think that's not surprising, right? Given that a lot of the common goals likely going to converge to kind of like a related designs. So I think one of the things that I would like to explore is if there's possibility on bringing things a bit together closely more. For example, how can some of the either having the AOTI be able to kind of interface with the ABI convention, or even have the type index and other things being unified. Add.
Okay, so I'm going to try to push the conversation along, and I'm going to put out what I see as like sort of the big major blockers here. So blocker 1 is the TVM ABI is trying to be independent of a backend. So like it's not just PyTorch that can do it, but really anyone else. You're going to have to convince us why we should care about supporting this use case, because it's just kind of like, especially for the stated goals of we want to make the PyTorch ecosystem be able to depend on ABI stable PyTorch. This is just sort of an extra level of generality that I mean, I guess if you're like flash attention and you want people to be able to use your stuff from other libraries, you might be interested in your thing. But remember, they have a best alternative to negotiated agreement, which is they can also just have bindings for your ABI thing, and
Mhm.
there's not as much incentive for us because people are going to bind against PyTorch anyway. So this is sorry. We're kind
Yeah,
of a
yeah,
big
yeah.
gorilla. So that I find is one challenge.
Okay.
The second challenge that I see is essentially it's related, but sort of on the different side, which is so I don't really think the header-only parts of the stable libtorch ABI are that big of a problem. But the other problem you're going to have is that we're going to just keep adding stuff. Like whenever there's something someone wants, and we're like, yeah, we got it from PyTorch. We're going to add a binding for that. And that'll just also, it'll also make it more difficult for like other backends to like implement, because the bigger an interface you do, right, the more difficult it is. And so like one of the things you see in the libtorch stable ABI stuff is that we're mostly doing vcalls everywhere. We're like, there's very little places where we're exposing structs directly. I guess stable I value is like one case
Yeah.
where we do that. But yeah. I mean, this is going to be slower, so
Mhm.
I don't know if we have done any rigorous benchmarking, but like this stuff is usually not the bottleneck, I think, for the kernels in question. All right, I've said my piece.
Yeah, so maybe let's try to address the second piece first, right? So in terms of like the I did do my homework and read this and indeed understand that in a lot of cases these are, instead of directly exposing a data structure, right? So it's kind of exposing functions that gets you the components of the data structure. I think this is the part where we can discuss and think about, for example, even in that's why when I talk about ABI convention, I love to, come and listen to what PyTorch folks are doing and work with you guys, right? Because I think the ABI itself of tensors, right? We could try to think about either, bring it up, even have a function call based function table mechanism that doing that. On the other hand, I can also imagine that, there is a need of adding things to tensors, but there's always a possibility of stabilizing a common header, right? So effectively you have a tensor class where you have like, shapes and D types and all the fields that are reasonably stabilized that don't need use function-based fetchings, but you still have a lot of the other fields behind the thing, right? That evolves very fast. I don't think there's a conflicting goal of you have to either expose a data structure or you have to expose a function, if that makes sense. Yeah.
Right, but okay, so let me put it very concretely. Would you like it if we changed AT::tensor impl so that it had a stable header on top that is accessible over C?
I think that will help us to align at least. Maybe let me put it another way, right? So if possible, my ultimate goal is if we can evolve the FFI tensor to an AT::tensor to share that common header.
Okay.
That would be the most ambitious step. But I know that would need a lot more conversation and
so
yeah.
Scott is some of the expert, and I am a little bit of the rest of the expert. So let me just like talk about like one problem. Like, so for example, we do like kind of nutty stuff in Tensor Impl. Like take sizes and strides, for example. The way we've done it is it's not a pointer to an integer that's allocated somewhere, right? It's the sizes and strides struct, which if it's small enough, we store them in line. Otherwise, it's allocated on the heap.
Yeah.
So I mean, all right. So like, yeah. So you're like, okay, we want to make this ABI stable. What exactly does that mean? Question mark.
So I think that would mean that you have a header that points to the struct and size, where effectively, that will certainly bloat the tensor ABI a bit. And
right. So, but the thing is that I don't want to like, we penny pinch every word on Tensor Impl. So like I don't actually want to like slam another cache line worth of info on it. Right, and so obviously we can do
Yeah.
a similar thing to like what you're doing with DLPack, which is on the fly, you allocate the struct that has the right, layout to go to the ABI. But like
that would kind of like I think that's a less ideal step for us.
I also agree.
Yeah. Ideally, you would like to directly take a stable tensor and go through ABI and call it a day. Okay. So that would be like one possibility, right? If you can have a header that contains the common set of information where you have size, shape, and then as you allocate your size, shape, you write through the possible informations. An alternative would be, you have a tensor where you have a V table that contains all the fetcher functions that you talk about, right? That would be an alternative that maybe not too ideal, but I think I would still, if possible, I would still even love to have a TV amplifier to be able to support such a version, right? So that we can do like a reasonably zero in memory exchange if needed. Yeah.
Go NYC.
I think I think I missed a little bit of the goal here. Why is the strategy we're using here, which is only one of the binary is the one that knows about Tensor and no one else knows about Tensor except through some ABI stable shim? Why would that not work for you?
It's less efficient.
It's
right?
less efficient. So yeah.
Okay.
Yeah.
It's just
Instead
it's
of,
just a
reading-
performance.
Yeah, it's a performance thing.
Okay.
Yeah.
Scott, I don't know if you have any like opinions or priors here about like how important this is.
I leave the high level planning stuff to folks like you, Ed. I just left a bunch of picky technical comments about the
Okay.
details on the down. Like, if you add indirection, it will go slower. That's like my high level opinion, but like people want some.
Okay, so let's talk about this vCalls table thing, which is possible. So I am willing to give you a double pointer indirection to a vCall table. Am I willing to put it at a deterministic spot? Scott, do you think we can make intrusive pointer ABI stable for C?
So the fundamental problem with being asked to make things ABI stable is like it requires us to like finish all our work on that data structure first. And we literally just changed the layout of intrusive pointer last week. That was one of the comments I left on the doc. If you had asked me to like, hey, are you super duper sure? I could have made this change like a while ago. There just like wasn't an impetus to do it. And in fact, the person who did do it was not me.
For the rest of the room, what exactly did we change?
The ref counts are now packed into a single 64-bit word, and we use one atomic instruction to inspect the word. And like for our increments, if we're touching the one that's in the high order bytes, we just add one shifted left 32 bits. And this is, we had a need to quickly inspect both of the ref counts in some critical paths.
Go, Jansel.
So we're solving a pretty similar problem for AOT inductor. So AOT inductor needs to have ABI compatible output binaries where you can like take the output of AOT inductor, you can change the PyTorch version and things still work.
Yeah.
And the way we do that is we turn Tensor into an opaque pointer where it's just like a void star.
Yeah.
And we have a bunch of defined C APIs for interacting with it. And I'd suggest reusing that stuff. I think that's a easier to maintain solution and one that already exists.
Jensel, that is just this doc, right? Like that is this thing that is currently getting shared. Like it's the shim.h and
yeah. I think we should just use this. I don't think we should try to change.
Let me reformulate Jansel's question, which is Tianchi, what would it take to convince you that a vCall based put on symbols style ABI stable interface is the right thing? Like tell me like what are the barriers on your end to wanting to adopt a design like this? So you do function calls for everything, very few structs.
Yeah.
And you they're done by symbols. So we're not hanging things off on the
I think what I would say is that, first of all, thank you very much for this conversation. I think this is gonna help me to get a sense of what is possible and the thinking of PyTorch developer here, right? So if that would entail that maybe in the FFI we are going to introduce something like indirect tensor that contains the effectively the object header v table that gets you all the field, right? And then that means that a compiler developer should be able to directly work with. That would be a bit more in directions, right? So originally, if you are writing a compiler, what you do is you read out the DO tensor in a single shot, and you inspect that DO tensor, which is kind of easier when you write a compiler on top of that. But if we have a symbol, what is going to entail is that we are going to effectively read out each of the field separately through the indirect function pointer, right? So that's the only difference. But I think if that is what you are throwing out, I think one possibility is in the FFI, if we can have a first class, indirect tensor that effectively aligns with the stable at.stable tensor, right? And go from there, if that makes sense.
I'm trying to.
Yeah, I guess, can I ask a question then?
Yeah.
Yeah, I guess the question I have is, Tianchi, if we are down for indirection, like the reason I was like, oh, maybe this is a different use case is because indirection was, for whatever reason, not okay. But why not reuse like stable tensor that already exists? Or what is preventing FFI from like consolidating on that?
So the main reason is, first of all, we like to align on a structure, right? That means that ideally, if stable tensor and FFI share the same ABI, that would be great. On the other hand, the FFI design is meant to be minimized so that ideally when a compiler targets the particular ABI, we don't have to operate on C++, we just operate on that ABI convention, right? So that's the only design constraint that we have. And and another thing is that I think ideally our object is intrusive, right? So we have like the reference counter and type index, so that you will be able to directly pass object across ABI boundaries while still being recognizable on the other side. I think it would be ideal if some of the structures, maybe not all structures, like from on a stable ABI side, will be able to have that common ABI so that we will be able to kind of pass things around in a more without introducing any indirection. Yeah.
Why have a quick
Why do you need something new here? Like I feel like the things we already have meet all those criteria.
Chancellor, I'll answer that. Tianchi wants a more efficient ABI. Whether or not you care about a more efficient ABI is like a question of requirements. But like, I do think it is very reasonable to look at the AOTI ABI and be like, man, this is like not very efficient. Like I think that is a totally reasonable reaction to have. But like, I think it would also be a very reasonable argument to say we don't care because this is not actually critical.
Yeah.
But like is this actually an efficiency bottleneck in the sense that like at runtime these are all going to get statically linked in or dynamically linked in and you're going to get like dynamic.
You can't inline anymore, right?
Yeah,
like,
you can't inline it.
Actually, Tianchi, do you have more numbers? Like, as in like what your target overhead is and like what your workloads look like? I think that would be very helpful for the room.
I see. So in my case, right, so the general thing is ideally, you want some exposure direct to Python that can be inline or not inline. In terms of numbers, like in terms of like a Python calling overhead, that would be like, the kind of the number that I'm looking at, right? So it's like 0.4 microsecond from Python.
But
While
there's an order of magnitude difference here, right? Because like if we turn this into a struct, we save a single C function call. The cost of a C function call is way cheaper than the cost of like a Python function call.
That's true. That's true.
I'm just not convinced that saving a single C function call when you're like calling in and out of Python is gonna matter at all.
No. So I think, Jason, the point here is not necessarily saving that the overhead of the function call, but I think it's more about, say, say I want to have a export of a library that gets shipped to, Tensor RT, and in that case, they want to be able to have like I think it's useful to have a reasonable minimum convention, right? Where you can say, okay, in this convention, you define most of the common things like tensors and other things, and as long as you interact with that minimum convention, a lot of powerful features can be built on top.
But that's already what we have. Like the stable like API is like a minimal convention for interacting with tensors.
By the way, Yankee, there's the stable tensor, which is the C++ layer on top of all of this. Would that solve part of your concern?
Oh, by the way, I'm not coming with the concern, right? So I'm more like, I'm coming with a proposal that I'm looking for ways to collaborate, right? Instead of saying that, hey, that's an existing concern in the design. I think the stable tensor design is a fair design that that leverages the existing AOTI ABI, right? So that you can get out the strides and other things out. And for example, one possibility that I can see here is even when we try to bring up the FFI, be able to interface with that mechanism, right? So yeah, so if that kind of stays
I see. Scott.
I think there's like a relevant question of fact here, right? Because so like the difference in like the worst case here is if like you have a consumer that really wishes it had structs and you have a function call based ABI, then like the worst case is you at the beginning of all of your interfacing with a tensor, you call all the functions and like materialize a struct full of the stuff you wanted to use, right? And like question of fact, how long would that take? I would estimate tens of nanoseconds. Would that roughly match your estimate, Tianqi?
I think that's kind of what we are doing right now through DLPack, right? And DLPack overhead is around about 20 nanoseconds in there. And so going through the ABI, so being fair, like we are kind of doing that today. That's why we are able to get this minimum PyTorch overhead, right? Which we love to upstream and making sure that it works well with. But I'm personally also very excited about this minimum convention that I think hopefully there could be more synergies here, where maybe we can even, because even in DLPack there are still allocation deallocations every time, right? So I'm trying to kind of get rid of that allocation deallocation if possible. That would be ideal, but even if we cannot go that direction, I think having ability to be able to kind of like have like a support over the ABI in some way, something that I think would be nice. Yeah.
So just to be clear, you're stating that like your requirements include like saving that 20 nanoseconds.
My requirement.
Right, because that's the performance difference between using function call ABI and using a structure-based one, right? Like if those are your requirements, those are your requirements. I just want to be clear.
So I want to be clear. That's not necessarily my requirement, and I'm not saying that hey, we cannot go through a function call ABI, right? So that's why I'm first throwing out the current state right? I'm looking for example, if the feedback is ideally there is what I hear is ideally there might be some appetite for function call based ABI for minimum tensor. Right? I would love to work with some of folks here to be able to bring it up if possible.
Got it. I just thought that might be a useful way to quantify the overheads here.
Yeah, but if we want to get rid of the 20 nanosecond, let me see. What kind of confuses me is that sometimes because if you just do micro benchmark, it's kind of 20 nanoseconds, right? Using DLPAC. But as we started to kind of like do the DLPAC translation all the way, it goes through the Python interpreter all the things, versus the vanilla version, there's about 200 nanoseconds for 3 arguments. That means that maybe because of cache and other things, the overhead grows onto 70 nanoseconds per arguments translation. So yeah, so I think that might be still something to sort out here, but maybe it's not as simple as 20 nanoseconds.
I mean, if you really twisted my arm, I would guess that the main cost would actually be the indirection to go hit the tensor impl, which is on a different cache line, like missing cache over that.
Oh, to be fair, any call through the PyTorch dispatcher, which every op goes through, is 2 to 5 microseconds.
Wow.
FYI, every single op you call in PyTorch is in that order.
A lot of time not doing that, for the record.
Okay, I see. 2 to 5 microseconds. Oh yeah, so 2 to 5 microseconds. I see. Yeah.
And so and also like when we think about like how fast we need matrix multiply dispatch on Blackwell to be, it's like 10 microseconds is our budget.
So our use case, like originally that's also my budget when I designed FFI initially, like a 2 to 5 microsecond. But then we worked with FlashInfo to bring it up, and my team come back telling me that my RMS norm is running twice as slower. So that's why it kind of motivates me to kind of work quite hard. And in the past few weeks, we get it down to like 0.4 microsecond, which gets into a more acceptable regime.
Are you like doing CPU inference or something?
No. It's just like the RMS norm kernel of Blackwell is 2 microsecond. And then if your API overhead is 2 microsecond, that gives you 4 microsecond, right? So it's nice to have. Like in practice, people still try to choreography most of the things, right? But if you're like doing LM inference and you have all those like RMS norm kernel sticking around and you are getting that extra overhead, you want to shave it off. Like at least we want to shave it off. Then that's kind of one motivation there. Yeah.
Natalia's in the call. I don't know if you have any thoughts.
No, nothing specific. I think you guys discussed what I was interested in.
Okay, then let me ask you a specific question, which is like, does this like RMS norm like example like make sense to you? Like we're in a like latency sensitive regime, I guess here.
Depends on the size. Yeah, it makes sense to me. I'm also of the opinion that PyTorch should not rely on third-party libraries for kernels like RMS norm. And it's a shame that NVIDIA doesn't work with us to provide native good performance and reserves it for some third-party packages.
I think my best offer is like, if you guys are like, we want to be able to inflate our stable struct from PyTorch so that we can do all the accesses in an inline way, so you're not just calling over and over. I think we'd be pretty happy to put that somewhere ABI stable. So you just have to do one vcall to get to it. Like, I don't think that would be a huge problem for us.
Do you think if it's possible to get one vcall to get entire tensor struct, like same as DLPAC, but instead of like so I think that is something that would be useful.
And maybe you can even stack allocate it so you don't have to go through malloc or something.
Yeah, that's what I was thinking.
If we're doing that, Ed, why not? Can we just create that object once. Okay, I assume the creation of a tensor object is already way above your budget. So I'm assuming the problem is repeatedly calling these attributes, because just allocating the tensor is going to be way more.
It's like that was relates to one of the RFC I put out a few weeks ago, right? So caching the output once, that overhead, I think as we measured, I remember is about 40 nanoseconds. Oh, not that much, like maybe around 10 nanoseconds. For fetching that, because there's a thread safety consideration there if you do lazily.
Right, but what I mean is based on the whatever stable API call we have, we could give you we can create a stable struct.
Okay. Yes, I think that is something could be helpful. Yeah, and if we can get one more stable DL tensor struct somewhere, that would be really helpful. Yeah.
Right, but I don't think we need libtorch to guarantee that struct being stable. We can build that on top of a stable API. And when you construct it, like for example, we could say the stable tensor layout, we could keep stable.
That I think the question there is, say in Python, get a PyTorch tensor, right? And I'm going to pass that PyTorch tensor to my function. I need a way to be able to fetch that stable struct from that PyTorch tensor, right? So right now we cannot do that because the Python directly interface with A10 as opposed to a stable tensor, right? So we kind of need to rely on the A10 DLPAC exchange mechanism to do that.
Oh, well, it depends how you do that extension point, I guess. But if you pass that tensor in, you grab the stable tensor out of it, and we can cache that field.
Yeah. So I think the main thing is we need a caching mechanism, right? If there's a caching mechanism that caches that efficiently, I think that's also kind of come back to the caching topic we discussed in light of the DLPAC thing. Yeah, that could speed up some of the access.
Okay. We are almost at time. I think we're going to get kicked out here.
All right. Well, let's continue the discussion offline. But thank you for coming to present. I'm sorry we couldn't give
Thanks for having
me. Oh yeah, we can just unify everything answer.
But that's what I understand, right? That's why. Yeah.
All right. Thank you very much.
Oh.
Cheers.
Yep.
Thanks.
Bye.